let's have a look at heat equation in higher dimensions. So higher dimensions, it's going to be as far as dimension 2. Earlier on, I said that a more complicated domain makes for a more complicated solution. You'll notice that complicated has a very low threshold. Even just going to a rectangle in 2 dimensions makes our problem so much more complicated than it has been up to now. So this is a fully 2-dimensional equation. We want to solve for omega being a rectangle in C2. We want to give an initial condition, and we impose boundary conditions being 0 at the top, left, and bottom, and non-zero for x equal to a and from y going from 0 to b. So there we impose a boundary condition that depends on y. And the steps are going to go as before: find the steady state solution first and find the transient solution later. So let's look at the steady state solution. So we drop the derivative with respect to time, and we're looking for a function v that only depends on x and y. We have that minus nabla squared v is equal to 0 on omega. We have that v for x equal to 0 and y is equal to 0. For x equal to a and y, then we have v equals to f of y. And for v for any x and y equals to 0 or b, then we have 0 boundary conditions. So I'm retracing the boundary conditions that I had introduced before, but in formulas. And now, instead of an ODE for v, instead of something very easy and trivial as we had before, now we have a Laplace equation for v. This is not as straightforward as we would like it to be. It's actually a PDE itself. So we have to first solve the Laplace equation in order to be able to solve the heat equation in 2D. Once we have the solution of the Laplace equation in 2D, then we can use it to build a steady state. And by linearity, we know that the full solution is the sum of the steady state plus the transient state. But the transient state itself will be really not that straightforward to actually build. And the transient state will have homogeneous boundary conditions. So the transient state has to satisfy Vt minus nabla squared, Wt minus nabla squared W equal to 0 on omega. W on the boundary is equal to 0, and W at time 0 is equal to our steady state, our initial condition minus the steady state. Then we have that U summing the steady state and the transient state satisfies the original problem. But as you see, going from 1D to 2D in our domain really makes our problem so much more complicated than it used to be.